Topic 3.14, I know that this looks like a whole packet because I don't think I've ever given you notes this long. It's not that they're long, it's that I wanted to make the graphs big enough for us to see, so it just took multiple pages to create these notes. Okay, so don't panic by their length. But what we're going to do today is extend the idea we had from last class of plotting those polar coordinates with r comma theta and create actual functions out of these. To graph the graph of the function r equal to f of theta, which if you notice the input is an angle measurement and the output is a radius, in polar coordinates consists of the input-output pairs of values r comma theta, where the input values are angle measures in radians, and the output values are radius lengths, so we're going to call that radii. Radius is made plural by putting two i's at the end of it, like cacti, radii. On the AP pre-calculus exams, questions may use the following phrasing to introduce a polar function. It might say something like, the graph of the polar function r equal to f of theta, where f of theta is equal to 3 minus 3 sine of theta, is shown in the polar coordinate system between 0 and 2 pi. This is an indicator that we're not using x and y coordinates, that you're going to have one of these web-looking graphs with all the circles radiating out from the origin. That's your cue that we're switching into a polar coordinate system as opposed to the xy coordinate system. So what I've done for you here in example 1 is I've actually found all of the values for the function 4 plus 4 cosine of theta, all of the radius lengths, if I were to plug in all of my, quote, important points from around the unit circle for between 0 and 2 pi. So I'm talking 0, pi over 6, pi over 4, pi over 3. We see how this works? And I went ahead and evaluated it for you, so we didn't spend any time on that. You're welcome. Basically, I said, okay, plug in 0. What is the cosine of 0? That's 1. 1 times 4 is 4. 4 plus 4 is 8. So I'm getting all these values by actually doing the math here. What we're going to spend time doing is plotting each of these points. So we're reviewing how to plot polar coordinates while creating an actual function. So our first coordinate point is angle 0, 0, 8, angle 0, radius 8. Angle 0 is your positive x-axis, and we're going to go all the way to radius 8. So we're at 8, 0. Now here's what's interesting, and I want you to, I already see some faces going, but that says 0, 8. Why did you just say 8, 0? Great point. Our input value is theta. Our output value is radius. However, when we write down the coordinate points for any polar coordinate, it is r comma theta, which means technically instead of calling these input-output pairs, we should really call them output-input pairs because the output actually comes first and then the input comes second. So that's backwards from an xy coordinate system. So keep that in mind when I'm talking about these points. The next coordinate point we're plotting is 7.641 comma pi over 6. So I'm going to a radius length of 7.5-ish, so it's going to be like halfway between 7 and 8, and I'm going to go to the angle pi over 6. So I'm going to put a coordinate point right here. So boom. My next coordinate point is 6.82 comma pi over 4. So I'm going to go to 6.82, so it's a little bit under 7, and put a dot at pi over 4. Do you see what I'm doing here? Like I'm just plotting these points. The next coordinate point is radius 6, angle pi over 3. So I went to 6 comma pi over 3. We're going to do this all the way around our unit circle. So all of those values of angles that we've deemed important all the way around our unit circle, we're going to find those points. The next coordinate point is 4 comma pi over 2. The next coordinate point is 2 comma 2 pi over 3. The next coordinate point is 1.1 comma 3 pi over 4. So just give me as close to 1.17 as you can. Then we have 0.5359 comma 5 pi over 6. I'm going to do my best. That was a lot of numbers. Correct. That was this coordinate point right here. 5.539, so about 0.5. And then angle 5 pi over 6. Do we see what I'm doing? Still no? Thank you for your honesty. Let's try the next one. Let's plot this coordinate point. What is the radius length? What's the angle? Well, if I'm at radius 0, that means I'm at the origin. So I'm going to plot this next coordinate point right there. I already see, yes, actually. Kaylin says, is it going with her hand doing this? Yes. Polar coordinates end up looking like flowers or hearts or circles. Not quite circles, they always have a little dent in them. Okay, the next one is at 0.5-ish, comma, 7 pi over 6. So I'm going to a radius length of 0.5, and I'm going to be at the angle 7 pi over 6. The next one is 1.1-ish, comma, 5 pi over 4. So 1.1-ish, and then 5 pi over 4 would get you like here-ish. Ish. Yeah, we're plotting some irrational numbers here, so like we're doing our best. And then 2 comma 4 pi over 3. 2, I can do 2, and then 4 pi over 3, boom, right there. The next coordinate point, if I go back to the next table, I just made this 4 tables to make it fit. 4 comma 3 pi over 2, so that's a radius of 4 and an angle of 3 pi over 2. Bless you. Radius 6 comma 5 pi over 3, so 5 pi over 3 and then 6. 6.8284, so 6.8 just under 7, and 7 pi over 4. 7.46, so that's about 7.5, and then 11 pi over 6. And then I have radius 8, angle 2 pi. What's already there? The same dot. So 8 comma 0, or sorry, yeah, 8 comma 0 and 8 comma 2 pi are the same point because they're the same angle around my unit circle, same revolution. Okay, let's play connect the dots here. And you're like, literally how, Miss Quigley? Great question. We're going to start where we started with the angle, which means we're starting around the unit circle, going in the positive angular direction. So we're connecting the dots. Oh, boom. Oh, I missed one. You get it. Like this. Oh, it's so cute. What does it kind of look like? A sideways heart. You know what's cool? This is a fun fact you don't have to know for this class, but I think it's cool. This is called a cardioid. What do you see at the beginning of the word cardioid? A heart. Cardio. Heart. Ah, look at that. Science and math overlapping. It looks like a beach. Okay. So what exactly happened here? And how do we make this something that we understand? Thank you so much for asking. If we look at the function we were graphing, what kind of trig function are we graphing? Cosine. Think back to when we did cosine when it looked like a wave. Did cosine start at the middle or at a maximum value? Maximum. And if we were looking at this one, what would the amplitude of this function be? What would the midline be? 4. So what I've done for you is I've actually graphed that cosine function down here next to you. So if you see, I have a midline at 4, right? An amplitude of 4, and it's a cosine function. What we have done is we have taken the rectangular version of 4 plus 4 cosine of x and graphed it in a polar coordinate as 4 plus 4 cosine of theta, where it's equal to r instead of equal to y. So we're in an r comma theta instead of x comma y. But there is a really big relationship between the 4 parts of the cosine function and the 4 parts of the polar function. Follow along in this color code with me. Pink. The first section between 0 and pi over 2 of your cosine function is the part of this graph that is concave down and decreasing. You remember that vocabulary from Unit 1? Concave down and decreasing. That same set of intervals, those same angles between 0 and pi over 2 is this table right here, specifically. And that table corresponds to only one section of my polar graph. Corresponds to this section. The second part of my cosine function is going to be the part of this cosine function that is concave up but decreasing. So that's between pi over 2 and pi. If we look at that in regards to the polar version of this function, That's the second table, those angles between pi over 2 and pi, and that corresponds to this section of the polar function. You can kind of see what's happening here. The third part of the cosine function, which I'm going to do in green, is concave up and increasing. It corresponds to the angles between pi and 3 pi over 2, which in my tables, oh look, pi and 3 pi over 2, those angles between them would be here in this table. And that table gave us this little section of the cardioid. And then last but not least, we have a section of the original xy coordinate plane cosine function from 3 pi over 2 all the way back to 2 pi. That corresponds to my last table here, between 3 pi over 2 and 2 pi, which also corresponds to the last section of the cardioid, the last section of this polar function that we graphed between 0 and 2 pi.
So is it a longer, is the peak interval longer because they have more values?
Not necessarily. It's that the radius is changing differently there. And we're going to talk about the rates of change of these graphs next time. So hang on to that idea because we're going to explore that next class. Okay, one of the main concepts that we're working with today, don't flip it over yet, is thinking about polar functions which are new and maybe scary in terms of the xy version of the same equation, because we understand a lot more about that equation. We're more comfortable there. We've worked in the xy plane since like kindergarten when we started plotting points. I know you didn't start that in kindergarten, but you know what I mean. Polar functions are new, so we're going to tie it to things that we understand a bit better so that they're not as overwhelming. Okay? Can I show you some examples of what we've seen as multiple choice questions with polar functions so we can see how to start reading these graphs and answering questions? When working with multiple choice questions involving polar functions, it is advantageous to evaluate the function at several values of theta, easy values of theta, like 0, or something you can relatively easily read on a graph given to you. Utilizing the multiple choice options can be helpful when determining which values of theta to consider. So in example 2 here, I've actually worked this one entirely out. That's why it looks like there's a whole lot of writing here. It's because it's a multiple choice question with my work typed on here. It says the figure shows the graph of the polar function r equal to f of theta between 0 and 2 pi in the polar coordinate system. Which of the following could be an expression for f of theta? So first things first, when we're looking at these graphs, I always want you to try to figure out what the radius is when the angle is 0. The angle is 0 when we are touching the positive x-axis. Is there a dot on the positive x-axis? No, so what do you think? What conclusion can we draw about the radius length when we're at 0 for the angle? It's 0. Do we have a coordinate point here? And I'm just using pink so it shows up. This is not like a color on purpose. This is the coordinate point 0, 0, radius of 0, angle of 0. If we had a dot on our positive x-axis, that would be the radius when the angle is 0. So we're going to use that information and we're going to plug in the number 0 to each and every one of my questions here to see which one of these best represents this function. So if you see in each of those answer choices, the first thing I did was take the expression in the answer choice that might make this graph, and I plugged in 0. In this first one, 0 times 3 is still 0. The sign of 0 is 0. And 3 times 0 is 0. So we keep answer choice A. We keep answer choice B for the same reason. But answer choice C and D, when I take the cosine of 0, the cosine of 0 is 1. So this is trying to tell me that I have a radius of 3 when my angle is 0. Is that true? Do I have a radius of 3 when my angle is 0? No. So we would smartly, whatever, you get it. We would eliminate C and D. Now, of course, we need to find another angle that we can plug in, and then the world's your oyster here. I like to choose the easiest angle to see, or the first angle that I see, which the next first angle that I see a ideal coordinate point for is right there. because it's like all the way out to 3. So I know that the radius here is 3. What's the angle? Pi over 6. So I want to be able to plug in the angle pi over 6 to one of these expressions and get out the radius of 3. But I only have to plug it into 2 answer choices here because I eliminated 2 more. And when I do that, again, I still have to know all of my unit circle things here. 3 times pi over 6 is pi over 2. Sine of pi over 2 is 1. And 3 times 1 is 3. So answer choice A is good. If we look at answer choice B, same vibe in the middle. Sine of pi over 2 is 1. But negative 3 times 1 is negative 3. Is that the right radius length for angle pi over 6? No. So we can eliminate this answer choice and say that answer choice A is the one that best represents this graph. Questions, comments, concerns? You're about to try one. Same question, new graph is right here below it. I'll help you find the first angle we should plug in, but then the rest is yours. It says here, the figure shows the graph of the polar function r equal to f of theta between 0 and 2 pi in the polar coordinate system. Which of the following could be an expression for f of theta? Let's look at angle 0, which means we're looking at the positive x-axis. Is there a dot on the positive x-axis? Yeah, what radius is it? So we're looking to see if we can find one of these functions that when I plug in 0, I get 2. This is r, this is theta. That's where you're going to start. Plugging in 0 for theta, seeing which one of these will give you 2. After that, most likely you'll eliminate it down to 2 answer choices, and I'm going to let you choose from there what other angle you plug in. Go for it. You got this. Here's what we should have done for this one, maybe. If we plug in the angle 0, we'd have 2 plus 4 times the sine of 0. And what is the sine of 0? 0. So this is 2 plus 4 times 0. Oh my gosh, please follow PEMDAS. Do not add 4 plus 2. You have to multiply 4 times 0 before you add the 2. 4 times 0 is 0, and 0 plus 2 is 2. So that one's good. We're going to keep that. We repeat the same process here, plugging in the angle 0 for the second answer choice. This would be 2 minus 4 times 0, which still gives you 2. For the third one, 2 plus 4 times the cosine of 0. What is the cosine of 0? 1. So then we're doing 2 plus 4 times 1. 4 times 1 is 4, plus 2 is 6. Don't want 6 there, so I'm going to get rid of that one.
The cosine of 0
is 1. Horizontal displacement at angle 0. We're 1 away from the center.
Oh, at angle 0.
Yeah, correct.
I don't know why my brain.
2 minus 4 times the cosine of 0 again, when we know cosine of 0 is 1. Or I've told you cosine of 0 is 1, which means this ends up being negative 2. It's also not what we want. So goodbye. Okay, we only have 2 answer choices left. Here comes the part where we have to make a choice. And this is mathematician's choice here. We need to choose another coordinate point on this graph to verify that it's returning the right angle, or the right radius. So we have a few options here. You could have picked this angle. You could have picked this angle. You could have picked this angle. If I were to label all of these points, this one would be 2 comma pi. This one would be 2 comma, negative 2, sorry, comma pi over 2. Should that be negative 2? No, it should be positive. This one would be 2 comma 3 pi over 2. One of those things you can plug in. Yes. Where? What? What? Oh, radius value being 0 means we're on the origin. Because radius of 0 means we didn't move from the origin. Because it's, yeah, remember, it's the rings. Think about it as rings. Yeah, it's confusing. I get it. So we're going to plug in one of these other angles. I'm going to plug in 3 pi over 2. I personally like to choose something at the ends of my graphs to plug in because I find it just simpler for me, mathematicians-wise. You can plug in whatever you wanted. I like to plug in outside the largest angles I can find. Don't know why. It's just a thing for me. So for this one, I'm going to do 2 plus 4 times the sine of 3 pi over 2.
Wait, then your furthest one is. Why is the furthest one 6, right?
Yes. Thank you so much. It's Monday on a Tuesday. What? It's Tuesday, guys, even though it's the first day of the school week. Don't do that to me.
Your point.
I'm not coming to school for the rest of it.
Yikes. Okay, which if we do the sign of 3 pi over 2, that's -1. And then 2 plus 4 times -1, that ends up being -2. That's not what we want. So we're going to really hope B is correct. This time we're doing 2 minus 4 times the sine of 3 pi over 2. And the sine of 3 pi over 2 is -1. -4 times -1 is +4, plus 2 is 6, which, hooray, gets me answer choice B. Here's another fun fact for you. That first graph on the very front was called a cardioid. This graph, because it has an extra loop in the center, you don't have to know this, I think it's just fun, is called a limaison. That is a French letter that we don't have in our alphabet, limaison, which I think is fun to say. Say limaison. And then if we were really naming all of them, what does this kind of look like to you guys? Okay, maybe I walked right into that one. What if it had more petals like this? What does it look like? A flower. This is called a rose curve, which is just fun.
That's basic. The other ones are cool.
Okay, I just think that's fun. There's more names for more of the different types of polar graphs we can draw. Those are the ones you see the most. Also, it's not important that you know the names of them. I just think it's fun. What I do think is important, though, is that we really nail down the connection between a polar graph and its rectangular counterpart. So what I've done is I've graphed for you the polar functions. Look at that rose curve. On a polar coordinate grid, and then I've also graphed the rectangular functions with the same A, B, C, and D values. So it takes the amplitude, the displacement, the period, the phase shift that you would have had in the polar function and puts it on a rectangular screen. So basically, instead of R and theta, I just made them X's and Y's, which produces a different kind of graph. We want to highlight the 4 portions of each graph that correspond to the 4 parts of one period for the function. So what I mean by that is, just like we did on the front, I want to highlight the 4 different concavities and increasing, decreasing sections of one period of the XY plane. So there's one full period, right? We have increasing concave down, decreasing concave down, decreasing concave up, and increasing concave up. And we're going to find those same corresponding pieces of this rose curve of the polar function so you can see how it is created. Before I get going, something that might be helpful, between 0 and 2 pi on this rectangular curve, how many full periods do you see between 0 and 2 pi? I see 1, 2, 3, 4. This is a frequency of 4 over 2 pi, 4 in every 2 pi. That's going to be helpful for thinking about our polar function. Our polar function is always going to start at 0. So I want you to put your pencil or pointer feeder at 0 here. This is angle 0. There's no coordinate point out here, so we know it's at the origin. We do need to be traveling around. Everybody look at me for a second. I'm going to face this way so I'm facing the same way as you. Like this. Why do we think we want to go this direction? What also goes this direction? It's counterclockwise. What also goes counterclockwise? The unit circle. Great. We're going to keep that idea this whole time. So the idea of doing a counterclockwise rotation with your hand is going to be very helpful. If I start at the origin and have to travel counterclockwise, the first piece of this polar function I'm going to graph is right here. If I follow that around, I'm going to switch to blue or whatever color you're using for your second interval. And where do you think I should color blue? The next ending of that petal. Ooh, yikes. Here's where it gets confusing, okay? So I went away from the axis. I came back. What happens next? I go away. So if I'm doing this, the next one goes here. We're doing this, right? So if I come here and I'm coming back down here, where's the only other place to keep that pattern going? Right here.
Why do you go negative in both directions? -5,
Oh, wrong color, Miss Quigley. Yep.
Miss Quigley,
Yes.
on the XY coordinate graph,
Yes.
why does it go up to -5 and down to -5?
Oh, great question. What is the amplitude of this sine function?
5.
5. With no change in my midline. So it should go up to 5 and down to 5. That's a good point. Let me write down the XY version of this so we can see what we're doing. We're doing y equal to 5 sine of 4x. So we have an amplitude of 5 and a frequency of 4. Our period would be pi over 2. Let me answer the phone that just rang and I didn't answer. Yeah, I understand your question now. Yeah, it's just a screenshot from Desmos, so those lines look confusing. Okay, cool. If we're following this along, we went away from the x-axis, towards the x-axis, away from the x-axis. What's next? Towards the x-axis, which for us in a polar coordinate means we're getting closer to the origin. Here's another connection I want you to make. These values on the xy plane that are pink and red, what color is that? Blue. Pink and blue. Would you say that these are positive or negative output values? Positive. So look, we're above the x-axis. We're in positive outputs. And then down here, what happens? Negative. So look, what happens? We're below. Let's start to make these connections, shall we? Can we do another one? We're just doing this connection between the different graphs so that you can see we can always use xy coordinates to make polar functions more accessible for ourselves. Here's a cardioid here for us. This one's going to be easy on the cosine version, the xy plane. So this one is y equal to 3 plus 3 times the sine of x. Notice r and theta became x and y. If we color the 4 parts, 4 different concavity changes with increasings and decreasings, right? I guess concavity changes is the wrong word, but you get what I mean. We have a part here that's increasing concave down, decreasing concave down, decreasing concave up, increasing concave up. It takes an entire distance of 2 pi for this to finish one cycle. Let's apply this to the cardioid that we have here, to the polar function. The first section of my graph here was going away from the midline. So the first section of my cardioid that's going to be pink starts at 0, which means we're starting here at the positive x-axis and going around in a clockwise manner. We go away, then we come towards, then we go away, then we come towards that center line. There is a connection between these shapes that's very helpful to make when we're trying to understand polar functions, since we know a whole lot more about the xy coordinates. Last one on this page, we're going to color code 6 cosine of 2 theta and its corresponding xy coordinates, which is y equal to 6 cosine of 2 times x. So I've plotted both for you. If we start with the coordinates that are in the xy plane, this is cosine, so it starts at an output value. So we have the first section that is concave down and decreasing, concave up and increasing. Decreasing, concave up and increasing, concave down and increasing. Now, if I finish this one period, I only got to pi on this graph. How many full waves or full periods does it take for me to finish these shapes between 0 and 2 pi? 2. Keep that in mind. Our first little part of a graph here, we should start at 0, 6. So if we look here, we're at angle 0, radius 6. That means this is going to be the first start of this graph. And that makes sense because we're coming towards the x-axis, towards the center line, so we're getting closer to the origin. That's pink. If we follow the same ideas we've had where now we're going away from, we do need to swoop down to the bottom. So then we have this section. Then we're going to swoop up, so we're coming closer to the midline, closer to the origin, and then away from. What I find easiest when we're going to answer the questions like the ones on the next page is to think not really as a polar function, because we're not as comfortable with those, but really tie it back to the trig graph that we have in the xy coordinate plane, because we're going to be able to answer more questions that way. Now, I was making a big deal about this earlier and didn't provide the conclusions. How many of these would it have taken to finish the xy coordinate plane? 2. How many of these would it have taken to finish in the polar coordinate plane? 2. If we go back up to that rose curve up here, you guys told me there was 1, 2, 3, 4. 1, 2, 3, 4. So these frequencies do kind of help you create what are like the petals of these rose curves, or the number of loops you would have to finish between 0 and 2 pi. Okay, understanding these different intervals is going to help us answer questions like you'll see on the next page. Because when graphing coordinate polar functions, a lot of times I'm going to ask you to restrict the domain to only certain parts of the polar function. So maybe just like the top of one petal or the side of one petal, and we need to know what portion of our graph creates that particular point. So a question may say this. It says, example 5, a portion of the graph of the polar function r equal to f of theta, where f of theta is equal to -3 sine of theta, shown in the polar coordinate system between some numbers a and b. If a and b are both between 0 and 2 pi, which of the following could be the values for a and b? So we're saying that there is a whole graph happening here, but I've chopped it off between two numbers and I didn't tell you what those numbers are. I want to know what those numbers could be. Now, the easiest way to do this is to take the polar function they gave you and graph it as a rectangular function. So in our little space right here, I actually want you to graph f of x equal to -3 sine of x. Now, a question for you. This is a sine function. Should it start at a maximum or a minimum? Or a midline? Midline, great. But it's -3, so what does that mean I should do here? It's got a -3 in front. I guess I should ask, what's the amplitude? We will start towards the bottom. So we do start at a midline. That's going to be the starting point for any sine function that doesn't have phase shift. But instead of going up, where should I go? Down. And down how far? -3, and then back to 0, and then up to 3, and then back to 0. This is one portion of this sine wave between 0 and 2 pi in the xy coordinate system. Now, we need to know which part of this wave corresponds to this part of the polar function. So if we were doing this concept, so again, I'm doing my fingers around in counterclockwise motion, would you agree with me that if I tracked this wave, that it would be going in this direction? Yes. So you would agree with me that we are getting closer to the origin from a negative value, because we're underneath, we're below the x-axis for this polar axis, yes? And we're getting closer to the origin. So we are looking for a portion of this graph that is negative, has negative outputs, it's underneath, and it's getting closer to the midline. Which section of this graph has that happening? Yeah. This is pi over 2 to pi. If we know the values of our unit circle, we know that this are the important points for a regular sine function. And so we know that the same portion that's shown in the polar graph is going to be between pi over 2 and pi. So B is the correct answer. If we translate it into an xy coordinate system, theoretically it's going to be easier to figure out where I've asked you to chop off this graph. I'm still going to do the second one with you because I feel like we still need B. Is that okay? You're welcome. Okay, example 6, a portion of the graph of the polar function r equal to f of theta, where f of theta is equal to 3 times 3 theta, is shown in the polar coordinate system between some a and b value, where a and b value are between 0 and 2 pi. or some chop of this graph between 0 and 2 pi. Which of the following could be the values for a and b? To do this, we want to graph f of x equal 3 times the cosine of 3x. So we have to remember some things from topic 3.6 and 7, or 4, 5, 6, and 7, when we started graphing sines and cosines. Cosines, does it start at a maximum or a minimum, or a midline? Maximum. What is going to be the maximum here? 3. There's no change to the displacement or the midline, so my amplitude being 3 means that I know this is going to start up here at 3. Now, the only other thing this has is a number inside the cosine function. What does a number multiplied inside the cosine function affect? What vocabulary word? Your options are amplitude, displacement, period, or phase shift. It does affect the period. Very good. We find the period by doing 2 pi divided by that number, which means I should end this entire graph at 2 pi over 3 if this is 0. Now, I still need to hit all 4 important points for this cosine function, which means the next tick mark would be a center, and then a minimum, and then a center, back up to my maximum to finish the entire wave for cosine between 0 and 2 pi over 3. I guess I should label this. Let's go ahead and just label the rest of these numbers because I think we're going to need that later. What is going to be halfway between 0 and 2 pi over 3? Pi over 3. If 2 pi over 3, we take half of it, it's regular pi over 3. And then what's halfway between 0 and pi over 3? Pi over 6. Which then means that this is 3 pi over 6, which does turn into pi over 2 when you reduce that fraction. Okay, let's answer the same questions. Ouch, stand up for this one. I just hit my knee really hard on that. If I'm following this in a counterclockwise pattern, would you agree with me that these arrows, if I was following along, it would be traveling this direction?
Yes.
Okay, which give me some descriptions. Are we traveling away or towards the origin? Towards the origin. And is it above or below? Above. So we're looking for a section that is above and traveling towards the midline, since we're traveling towards the origin. Which section of this graph is also, our xy coordinate, is also above and getting closer to the midline? This section right here, yes? Between 0 and pi over 6. It is easier to translate these into xy coordinate planes, which does mean that you have to remember all the things I taught you earlier in this unit about graphing trig functions. Ta-da! You ready for a hard one? Let's do it. Example 7 says the figure shows the graph of the polar function r equal to f of theta, where f of theta is equal to 6 times the cosine of 3 theta in the polar coordinate system between 0 and 2 pi. Have you noticed I've said that same sentence pretty much every problem? Those are going to be the same setup for the words to let you know we're talking about a polar function. Okay? It's not necessarily a domain restriction. It is, but because we're going between 0 and 2 pi usually, that just means you see an entire unit circle worth of the polar function. There are 4 points labeled A, B, C, and D. And if you can't see them, here's A, here's B, here's C, and then D is in here, in case you missed that one. If the domain of F is restricted to pi over 3 to 2 pi over 3, the portion of the given graph that remains consists of 2 pieces. One of those pieces is the portion of the graph in quadrant 3 from C to D. Okay, whoa, let's just make sure we know where that is. One of those pieces is a portion of the graph in quadrant 3 from C to D. That means I'm talking about this section. Question before I go on, why would I not be talking about this other part of this pedal? Yes, because why? We're doing this, yes? Is there any way I could go from C to D this direction if I'm going counterclockwise? No. So we know it's the C to D portion that follows a counterclockwise rotation. Okay, which of the following describes the other remaining piece is the question. We need to figure out what's happening at this interval. The interval they've told me we are restricting this to is between pi over 3 and 2 pi. So let's just quickly see what's happening at that interval. We're going to go back to some of the ideas we had from the first multiple choice question we saw. Let's plug in pi over 3, which means we're plugging 6 cosine of 3 times pi over 3 into our brains. If someone's like, where'd you get that from? This is the yellow highlighted equation that they gave me. I'm plugging in the first part of our restriction. What is 3 times pi over 3? Pi. So we're really asking what is 6 times the cosine of pi. What is the cosine of pi? Uh-oh, it's -1. Which means 6 times -1 is -6. So we should have a coordinate point of pi over 3, comma I said that backwards. -6, comma pi over 3. So if I start at -6 and travel pi over 3, what coordinate point am I at? C. This is the coordinate point -6, comma pi over 3. Now that makes sense because we already said that that pink portion is one of the sections of my graph. Let's see what's happening at the end, which means I'm going to plug in the second portion of this restriction, sorry. You get what I mean. So I'm plugging in 2 pi over 3 this time. So I'm doing 6 times the cosine of 3 times 2 pi over 3. Those 3's are going to cancel each other out. So I end up with 6 times the cosine of 2 pi. What is the cosine of 2 pi? Yes, it's like the cosine of 0, which is 1. And so 6 times 1 is 6. So I should have another coordinate point at 6, comma 2 pi over 3. Here's 6. We're going to 2 pi over 3. What coordinate point is at 6, comma 2 pi over 3? Hey, this is the coordinate point 6, comma 2 pi over 3. That is a weird looking 6. Okay, let me just try it all the way over. Say again? So, question for you. If you're understanding the concept of needing to move counterclockwise, so we're moving around this polar function like this. We would have started here, we go around, boom, boom. What's the only way to go from where I stopped to the first portion all the way to A? From D to A, right? C is the correct answer. The portion of the graph in quadrant 2 from D to A. This is tough. These are hard. This is a whole new coordinate system you've never seen. So don't get frustrated with yourself if you're like, what? It's okay. We know a lot about sines and cosine functions in the XY coordinate plane, so let that help you answer these questions. The other thing that can be nice and helpful about this, although I'll tell you right now, I'm pretty sure most of these questions that have to do with polar functions were not on the calculator allowed version of the AP test. There are skills in the calculator that we're going to need to learn to make these polar functions easy. I need you to follow along with me because here's stuff you've never done in your calculator before. So if you did not grab your calculator and walked in, go get it real fast. Again, though you won't need to graph functions on the AP Pre-Cal test, it is important to know how to use this since this is a tool that you have. And if it happens to be on the multiple choice calculator allowed section, let's use our resources. I'm going to teach you both how to do this in the TI, which is what you have on your desks right now, and on Desmos, because I 1000% know when you go home, the tool that you have at home is Desmos. So it's good to know how to do this for both. On the TI calculator, you're going to press Mode. You're going to scroll down till the section that has 4 choices that says function, parametric, polar, or SEQ. If you're using an old calculator, it will only say POL for polar, but you're selecting polar as the mode of function that we are graphing. as opposed to a rectangular x and y, we're going to be graphing polar. So maybe like circle that on your notes so you can see it, that this is what you're looking for right here, so that you can see that, right? Okay, that's important. This time now, once we're in polar, you can quit the mode screen. When you press y equals and you're in polar, does it say y equals anymore on your screen? No, what does it say?
Radius.
The radius equals. That's great because polar functions are r equal to something. Everybody right now type sine of x. I just want you to see what that looks like. Whoa. Did x show up? No, what showed up now? What is the input value for a polar function? Theta. You're now going to have thetas as your input. That's very important. And a good check for you if you like thought you were in polar and all of a sudden an x shows up, you're not in polar. Okay. You can type the function into R1 and it will graph for you, which is great. You can also adjust the restriction. You know how we adjusted the window, right, for our XY coordinates? If you go to window, you now have 3 new options here called theta min, theta max, and theta step. You really won't change theta step ever, but you totally can change the fact that we are currently looking at this function between 0 and 2 pi. So let's say your question wanted you to look at it between 0 and pi over 2. You would just change this maximum number to pi over 2, and it will restrict the graph for you on your screen. Before we do some practice problems, because I'm going to have you split the practice problems in half, you can do this on Desmos. Desmos has a polar setting that you've politely ignored. If you click on the gear or the tool, whatever this is called, what is this? The wrench? In the corner, the settings tool, there is an option for a polar grid. So you can see the polar functions on a polar grid. The only caveat here that you need to remember is that you have to type r equals or else it will graph a rectangular function if you type y equals. So you need to type r equals and you have to type theta instead of x. But all you have to do to get a theta is type theta and it will automatically change to a theta. It's programmed to do so. And then you will get the polar function in Desmos. I find it easier to actually do this on the calculator because I don't have to remember to put r or theta, like it automatically does it on the calculator. But I know when you go home, if you don't have one of these, Desmos is what you use. So here's how you do it on Desmos. What I want you to do for these functions, I'll do the first one with you and then you have the second or the last of them, is I want you to use the calculator to sketch what this function looks like. Then we're going to highlight the interval of the group stated. So I guess I should show you on my calculator what I want. Fabulous. What I want you to do is take what you see on your screen with this rose curve or propeller, as you guys are calling it. And I just want you to sketch it. It doesn't have to be perfect, but it does need to be close. So like, just do your best. Ooh, that's bad. Let me try again. Oh, okay. I'm so embarrassed. I'm going to show you guys. I don't have it up on the screen. Look at what I just drew. That's my second attempt. Hey, you didn't have to say oh like that. Come on. Okay, not my best, not my worst. But here's what I also want you to do. We need to identify which portion of this graph is restricted by what they've told us to restrict. So we're going to go to Window. And we're going to say we're only looking at this graph between 0, check, and pi over 2. So I'm going to change the theta max to pi over 2. Because it's going to stop graphing the function after we've reached the angle or the input value of pi over 2. When I press graph, it only shows me this portion. Yes? Is everybody there? I'll be there in a second. So what I want you to do is highlight in whatever color you want just the section of the graph that is shown when you restrict it. Okay, 1 second. Those of you who are getting it, let's try the rest of these practice problems on this page. Those of you who are having, I will come. I'm coming. We have all of these, but we should have paused on C. Why is C different than the rest of these graphs? It's not polar. So what do we need to do in our calculator to graph this one? Change it back to function, which is our rectangular coordinate system. And then we can graph it because you're right, an X showed up instead of a theta. That means we're in rectangular rather than polar. So good pausing, good question.